Hello everyone. In this video of vibrations, we are going to look at the damped wave equation for a rope. If you watch my channel, under playlist vibrations, you probably have seen this video, theory and simulation of string vibrations or rope, where I showed you the solution to the wave equation in a rope, but that wave equation had no damping in it. So when you give it an initial condition and let it go, it keeps oscillating forever. In practice, everything has structural or other types of damping in it, including the two fixed ends. And so the energy of the string will be dissipated fast and it stops vibrating. You can look at a guitar, right? The string on a guitar or any other type of musical instrument with the strings. You can see that if you pluck them, give them initial condition and let them go, they would stop vibrating after a few seconds or so. So here, this is what we are going to focus on, a damped wave equation. So this was the wave equation, right? Where c was the speed of the wave, square root of t over rho. T was the tension in the rope, rho was the mass density. Now here we are going to add a viscous damping proportional to the velocity. Velocity of any point on a rope at any point is partial of y with respect to t, where y is the solution, is the transverse displacement. So derivative of that with respect to time is velocity. And if you multiply that by any constant, that is a linear or viscous damping, which here I show it by 2 beta. And if that's the case, then I would add that here on the basically right-hand side with the negative sign, or I can take it back to the left-hand side and make it positive sign. And then that term will be plus gamma partial of y with respect to t, where gamma is this damping constant 2 beta over rho, which was the density of the mass density of the rope. So now the damped wave equation, which is this one, has two constants in it, a c squared and a rho, correct? So c squared, as we know, is t over rho. So it's like rho is over here and t is over there. And as I said, if you bring that term, you're going to get something like this. And for that reason, we have to divide now both sides by a rho. And if you bring this negative term to this side, then that is your gamma, and this is your c squared, and that rho goes away because you divide both sides by a rho, and you get the damped wave equation. Now, how would you solve this damped wave equation? There is analytic solution by separation of variables, and there is numerical solution, let's say, with finite difference. Or you can use finite element. Here, I want to focus on finite difference, which is easier to talk about in this video. So here we assume that the solution has two parts, a spatial part and a temporal part, or a x and t. And then I plug them into the equation, and then once you do that, this is going to be your equation like this, where prime here means a derivative, correct? So for x it means x derivative, and for t it means a t derivative. So if you do that and then separate both sides, then one side will have only time functions, one side will only have x functions. The only way these two are equal is if they are both equal to a constant, and you can show that the only kind of constant that works in this case is a negative constant. Okay, otherwise this solution will not work with the boundary condition. And here, for simplicity, we assume that the rope is fixed on both ends. So y at x of 0 and y at x of L at any time point, they are equal to 0. Okay, so these are the initial the boundary conditions that we are going to use. So, and the only, as I said, possible lambda that works on that under that case is a negative lambda. If that's the case, then from setting the time part to the negative lambda, you get one equation. From setting the x part to the negative lambda, you get another equation, and these are those two separate ODEs. So you converted your PDE into two separated ODEs, and now each one can be solved with their own condition. So this is an equation in terms of x. So for that to be solved, you need the boundary condition. So that means clearly x at 0 should be 0, x at L should be 0. Correct? And then the time part is going to be a second order ODE, but there is a linear term as well. But if you form the characteristic equation for this, which is s squared plus gamma s plus lambda, then of course you get a damped solution for the time as well. So it's going to be a damped harmonic for the time, and it's going to be a simple harmonic for the x. And clearly the simple harmonic for the x is going to be a sine function like this, where the frequency is going to be n pi over L, okay? So if you set this lambda equal to n pi c over L squared, okay? So you set this equal to n pi, let me write it for you, c squared over L squared, then that c and this c would cancel. And so you can see that this guy here, n pi over L squared, this is your omega n, omega of the x function squared. And that is exactly, you see the square root of that right here. That is your omega. So that is your x solution. These are your eigenfunctions. These are the shape of the vibrations, different modes of it. Of course, you know you have infinitely many frequencies and infinitely many mode shapes. This system has infinitely many degrees. It's a continuous system where these guys here are your natural frequencies and these guys are your mode shapes. And then, as I said, your time function is going to be a damped harmonic. Now you're going to have both sine and cosine term in it. And these constant an and bn are, of course, found by plugging in the initial conditions. So y at x of 0 is f of x, your initial displacement along this rope. And this is y of t, seems like I missed the t. Y of t at x of 0 is g of x, initial velocity. Many times you start with 0 initial velocity, but you don't have to. And if you do so, then your an and bn can be found by these Fourier series, correct? So all you need is to go ahead and plug in t of 0 in this. If you plug in t of 0, then this term goes away. That term just becomes an. This becomes a 1. So you get basically y of x of 0, which in this case, this is f of x. So f of x is going to be summation n1 from to infinity of an sine of n pi xl. So for finding an, you need to multiply fx by this eigenfunction and integrate it from 0 to L and divided by L times 2. That is your an. Then you need to take a time derivative of this and set it to 0. When you take a time derivative, this guy here will show itself, okay? This guy here, the omega n comes out, okay? And this guy, omega n, also comes out, and this guy here will have a time derivative. So here, you're gonna have a lot of different terms. So you're gonna have this exponential times cosine and exponential times sine. And so you basically will have three terms that can have time derivatives. So your time derivative of y with respect to t, this y of t that we talked about earlier, this one, this y of t will have four terms in it: derivative of exponential times cosine, exponential times derivative of cosine, derivative of exponential times sine, and exponential times derivative of sine. And two of them will be 0, two of them will not. So you're going to have two sets of terms in this. And since you already found an, you can use it to now find bn by another sine Fourier series. Okay? So you can find the constant, plug them back, and guess what? Now you have your full solution. So your full analytical solution is going to be this one in 10, where basically gamma is defined earlier. Okay? So everything in it is known. Gamma is defined. That is your gamma, an and bn already found earlier. Now, one thing I have to emphasize here that could be a little bit confusing for you in this notation is you might say omega n. What is omega n? So here, this omega that you see in the temporal solution is this one. And you might say, you already told me that this guy under this, inside the sine function, that frequency, that is your omega. So do you have two omegas? Yes. So one of them is omega n, the frequency without damping. I guess it's appropriate in this case for me to use a different notation for this one. I think based on my previous lectures, I should really call this guy omega d, not omega n. This is the vibration frequency when there is damping. So that is really omega d that you have here. This lambda n is omega n squared, okay? Right? Of course, times c squared. So this guy here, this frequency in the spatial solution, that is the natural frequency with no damping. And then this one here is frequency with damping. So if that is the case, then I would like to call these also omega d. Okay, that is basically a lot more appropriate to call it the damp frequency instead of just calling it also omega n. So there we go. You have your final solution. Everything in it, as I said, is perfectly known. And you can basically plot this if you want. The only thing is you can never keep adding these mode shapes forever. You have to stop at some point. You have to decide how many mode shapes you want to add, right? And that is where your approximation starts. But if you use enough of mode shapes, typically the approximation is very close to the closed form solution if there is one. So if your initial displacement matches one of these eigenfunctions perfectly, then only one of them will be activated. Otherwise, when you have a bunch of them, then you have to stop counting these mode shapes at some point. The other way to solve it is a finite difference solution where you approximate your second derivative with respect to time, with respect to first derivative with respect to time, and second derivative with respect to x. You plug them into the original ODE, which is this guy here. And then if you do so and solve for the value of the nodal displacement at the next time point, so here n corresponds to time and j corresponds to the location. So if you want at node j and at time n plus 1, you can solve it based on whatever that node was at the current time point and the previous time point, and of course the neighboring, these two, the neighboring nodes, the one right before it and the one after it. And of course you have this scalar r squared, which is c delta t over delta x, and clearly this one is unitless. If you want to get the stable solution, this r has to be less than 1, okay? If it is less than 1, so for a specific delta x and c, you pick a specific delta t, then you're good. Otherwise, if this condition is not satisfied, then your solution is not going to be stable. So typically these delta x's are not super big and this c is a big number, so your time steps should be very small, otherwise you won't get a good solution. Anyways, this is your update equation, this one, and all you need to do is to start it from some initial condition. So at time of 0, all of the nodes y of basically 0 and j, they all come from that f of x function, okay? So f of x, instead of x, you plug in basically y at j, right? Or y at I, that gives those initial nodal displacements. Also, since y of 0 and y of L are 0, so y of n at node 0 and y of n at the last node, whatever the last node is, let's say end node, these are always also 0 because these are the boundary conditions. And you keep updating and you can also solve that as I'm going to show you. One last thing I want to emphasize is if you looked at my video I just showed you, that I solved the wave equation in MATLAB with finite difference, for stability of the solution, we had the exact same condition that this ratio should be less than 1. So you might say here that we have an extra damping. We know that typically damping helps with the stability because it reduces the energy of the system over time. Can we pick a smaller r in this case, or a bigger r or something? Would we change this condition? And for instance, if I go with like r of 1.2 or less than 1.2, if I increase this number, which means I take bigger time steps, would that still guarantee a solution, a stable solution? No, you don't want to do that, okay? So here, adding that extra damping term does not allow you to take bigger time steps. And many times, actually, you see people even go less than or equal 0.9 instead of 1 just to be safe. So I do not recommend taking big time steps, and if you want to have a stable solution. Now here is the MATLAB code, and you see that the length of the rope is 1 meter. The C that I picked is 1, but you can make it a lot bigger, so you can give it a tension and a rho and calculate that if you want, right? So it is up to you. For instance, I say T is 100 Newton, and then maybe rho is also 100 in this case. And so C equals basically square root of T over rho. But again, feel free to change those T and rho to any number that you like. And gamma is also 1 here. Remember, it was 2 beta over rho. So you can also calculate that if you want. So for instance, you say in this case, since gamma is 1, that means 2 beta is also equal to rho. So beta should be like 50. Okay, so again, feel free to change these numbers. And then these are the numbers I have. So I have 100 nodes and then 1000 time steps, and the maximum time I have is 10 seconds. Okay, so 10 seconds divided by 1000 is your time step. Now here you calculate r, and you have to make sure your r is less than 1, and you see in this case when I ran it, the R was 0.98, so it's barely less than 1, so I'm good. If this is bigger than 1, what you need to do is to basically increase the number of time points or reduce the dt. Okay, if this is any bigger than 1, you have to add a thing here and say, for instance, if R is bigger than 1, then error, and say unstable solution, and then reduce the time step. Okay, so you can do that, so it gives you an error and doesn't run. Now here I pick my initial condition similar to one of the mode shapes. My initial velocity is 0, and then I solve both analytic solution and finite difference, and then I show them both on the same graph. Now, one thing that you're going to see here, similar to my previous video where I showed you analytical solution and numerical solution for a simply supported beam, and there was a phase difference or time difference between them, the same thing exists here. Okay, the same exact thing exists here, and basically that is because of the nature of finite element solution. Now here you saw that the amplitude of the vibration is going down. Look, over time it is slowing down and the vibration gets smaller and smaller, and the reason for that is damping. Now if you want to solve it for a bigger time, so instead of 10 seconds, right, you want to go, for instance, for 50 seconds, then clearly, since by changing Tmax I made my dt 5 times bigger, I need to bring it back by making this nt also 5 times bigger. So make this 5,000 steps. Okay, so make sure that your dt is not, and of course we put this check here to make sure that it doesn't happen. But clearly you see that here The analytical solution is almost at 0 now, and your basically numerical one is also getting to 0. As I said, there is a phase or time difference between them, but you clearly see that the system is stopping. Okay, and that is because of damping. So if you don't like to go for 50 seconds, maybe I just go to 25 seconds, and that should do the job. So I'm going to share this file for you on the video description, and feel free to play with it and learn from that. Hopefully this video was useful to you, and I'll see you in the next lecture. Thank you.